Afternoon. My name is Paul Fromme, and I'll be chairing today's webinar for the IMEC-E. So it's a pleasure to welcome you on behalf of the Aerospace Division, and more specifically, the Aerospace Materials and Structures Technical Committee, who is organizing today's webinar. And we are very fortunate to have Dr. Sarah Sharif Kodai from Imperial College London to present today on structural health monitoring of smart composite fuselage. To just give you a very brief background on her, she obtained her PhD from the Czech Technical University in Prague in 2008, and since then has been working at Imperial College London, where she is now a reader in structural integrity. Sarah, over to you. We're looking forward to a very interesting webinar.
Thanks very much, Paul. Can I just check with you that you can hear me okay?
Yes, we can hear you okay.
Okay, perfect. And I will share my screen as well. Can you also see my screen?
Yes.
Okay, great. I'll just put this down. Okay. There we go. So, good afternoon, everyone, and thanks very much to Paul and IMEC for this invite for the webinar. I'm very pleased to be talking today, although virtually. Oh, just give me a second. Yeah. So as Paul introduced, I'm Zara Sharif Kodai. I'm a reader at the Imperial College. And what I'm going to talk today about is structural health monitoring of smart composite fuselage. And it's really towards a building block approach that we have developed. But before I start the technical content, I just want to make some acknowledgement about the research findings that I'm presenting today. First of all the research that I'm presenting today in terms of structural health monitoring, and in particular the Clean Sky 2 project, ShareLock, has been all done with collaboration with Professor Ali Abadi, who is also at Aeronautics Department at the Imperial College. So I must really send my gratitude to him for collaborating for all the past years on structural health monitoring. We started with really developing the lab in the department from scratch. And I'm pleased to say that now we have a very well equipped lab with lots of different technologies related to SHM. So first of all, thanks for the collaboration, and I want to acknowledge him. And the second also is our research group, Structural Integrity and Health Monitoring, which I will introduce to you in a second. And also the results that I'm focusing on today mainly are from this Clean Sky 2 program, ShareLock project, which we've developed an extensive test scheme for SHM towards certification and industrialization. So that's really going to be the main theme of my talk. But before that, just to introduce you our research group in the department, which is called Structural Integrity and Health Monitoring. It's run by two academics, Professor Ali Abadi and myself. We have quite a dynamic research group. We have, I think, currently something like 4 postdocs and 14 PhD students from all around the world. This picture is a little bit old, unfortunately, because we haven't had the chance to all meet together and try to update. We've had new members join our team, and we are due to have a group photo together to try to update this. But nevertheless, just to introduce our research disciplines, is really focused on structural health monitoring, structural integrity and failure analysis, computational mechanics, structural reliability and optimization. But again, as I mentioned, the focus of today's talk is going to be on structural health monitoring and really introducing this building block approach, which is towards industrialization of these SHM technologies and methodologies. But before I dive into the technical content further, I like to start with, first of all, a motivation and also an introduction of what is structural health monitoring. Some of you may already be very well aware of what SHM is, but I think there might be people in the audience that don't know a lot of detail of structural health monitoring techniques. So I'm going to start with motivation and how, in particular, is going to have the SHM will have effect on damage tolerant design of composite structure, hopefully positive effects. So the first motivation is that you must all know that composites are being used more and more often in lots of engineering structures. From the service experience of composites and also the significant component testing that has happened so far, we know that the current aircraft structures made of composite have excellent resistance to environmental deterioration, as well as fatigue properties. So fatigue damage is not an issue for composite. So this means that in terms of damage tolerant design and also the maintenance planning, what is really critical for composite is the accidental damage. And what is accidental damage? Impact is an event that can lead to this accidental damage. And really, because we need to design for this accidental damage, we need to make sure that for the design is going to also be cost effective, especially for airliners, the design of composite. So this means that when we are designing the composite, the allowable damage limits must be set at their maximum allowable size while it maintains the ultimate load requirement. So what do we mean by this? If you look at the graph here, let me see if I can actually use the pointer. There we go. So when we look at the graph here, we are looking at the residual life of a structure, so how much load it can sustain based on different damage sizes. So we said that composites, we have to be aware of accidental damage. And in particular, what is quite challenging is the damage that is not detectable. And these are small damages which may not be found during visual inspection. And these are called barely visible impact damage. Now, there are different definition of what is BVID and how how to define it. This is one typical definition from Boeing, which is a typical dent depth 0.1 to 0.2 inches. But mainly the challenge of BVID is that during visual inspection that happens during maintenance, they will be extremely difficult and challenging to find them. So the damage tolerant design of composites says that your barely visible impact damage falls within these damage that are not detectable. So the limit between the detectable and non-detectable damage is the allowable damage. So this allowable damage must be set at the maximum, at its maximum, which is sustaining ultimate limit load. Now, for any damage larger than ADL, these are also classified into different categories, but these categories are really depending on the likelihood of damage detection. And this likelihood of damage detection is also directly established based on what is the non-destructive inspection technique that is used for detecting these damages, and also how much how it corresponds to this reduction in the strength. So now that we have an idea of what is allowable damage limit and what is barely visible impact damage, how can we then make sure that we are really designing our structure that is safe, but is also cost effective, because we need to allow for some damage to be some damage that it can happen in the composite and falls within this, that the non-damage, the damage that is not detectable. So at this case, what we want to really look at is this barely visible impact damage, and how can really SHM, sorry, how can SHM influence this damage tolerance of composite structure? So let's have a look at that. In this case, when we are designing different component parts for an aircraft, we know that there are probable impact that can happen on different sections of the aircraft. So if you look at this graph here from Airbus, you have the probability of having different impact events at different sections of the aircraft. Historically, the way that these data have been collected is based on metallic structure, because when there is impact on metallic, you really clearly see dents. And for example, around passenger door or cargo doors, these, because of, the usage of the door, you have quite a lot of probability of impact happening there. And when you measure these dents, the size and the dent of this impact, you can estimate, for example, what has been the energy of the impact event. So the design of composite, the way it's done at the moment, is that based on the probable impact events on that section, and also the level of energy. So you can see in this figure that based on different location on the aircraft, you have different impact events, and each of them will have different mass and velocity, which will result in different amount of energy. So based on the energy levels and based on the minimum damage size that can be detected, so this is the established detection the detection is based on your established inspection procedure. So what is the non-destructive inspection technique that is used during maintenance? We'll set this threshold of BVIT, and then you can see that you can go on a graph like this and pick what is the thickness of the composite. So what we hope to obtain from SHM really is to influence this design to become less conservative. So you can see clearly here, if we are able to detect smaller impact, barely visible impact damages in the structure, we can reduce the thickness or the conservative design of composite based on establishing smaller thresholds for damage detection. But at the same time, if we also can have a better estimation of impact energy levels for each of these sections, if we really know what are the limits of the impact energy, we can also influence the design in that way and result in thinner sections of composite. And we know that if thinner sections means that the structure is lighter and is also more sustainable towards the usage of, reducing the fuel consumption. So this is really how SHM can influence the damage tolerant design, hopefully in a positive way. So that's the motivation behind SHM. Now let's go into what is really structural health monitoring. So it is an alternative way of non-destructive inspection. And the idea here is that you have integrated sensors within your structure. So if you take an aircraft, you will integrate sensors which are permanently installed on the structure. And these sensors continuously monitor the response of a structure. So it's similar to human body's nervous system, where you have nerves distributed all over your body, and you can detect, for example, if there is an event that is hurting you, and in the same way, the sensors in the aircraft will also monitor the response of a structure. So this means that by enabling continuous monitoring of a structure, we move away from these inspection intervals, which are planned, and it's the current practice, and we only ground the plane and repair it only when there is an event that has happened, which has resulted in an impact that could have been characterized into an alert, and also could have resulted in damage. So in this way, what we hope to achieve with SHM is, rather than having intervals when you inspect the structure, is to have a continuous monitoring of the structure. And in that case, if there is going to be an impact event, we can design an early warning system. And this can be followed by an event where you can characterize and detect detect damage. So this shows any degradation that has happened in the structure. And it can then follow by the remaining useful life assessment, meaning that if we can detect the damage and also characterize it, we can say if there's going to be a maintenance action required for the aircraft. So at the moment, the inspection and maintenance expenses are something about 25% of the aircraft's life cycle cost. And this means that sometimes the inspection is unnecessary by grounding the plane just because it's based on scheduled intervals. But at the same time, the reliability of damage detection can also be improved because having sensors that are continuously monitoring the behavior of a structure, you also don't rely on the capabilities of the technician missing a damage that is present. So the reliability of the damage detection can also be increased while reducing the cost of inspection by going towards condition-based maintenance. Now, what are the components of SHM and how do we design such a system to be applicable to an aircraft structure? So there are three main components. There is diagnosis, prognosis, and life extension. And we'll see what each of them consists of. So the diagnosis part is really having the sensors that are distributed on the structure and gathering the information from the sensors and deciding how, what to do with this information that is coming from the sensors. The most important part is that we really need to comply with the probability of detection and the reliability, which is 90-95%, which is acceptable for non-destructive inspection. And what we need to demonstrate this is also that this is the 90-95% is under environmental and operational condition of an aircraft. So if we take, for example, the diagnosis part, the SHM system will have components which are airborne, and these are the permanently integrated sensors within the structure. So these sensors can be different types of sensors. We'll go through some of them in a second, but different types of sensors are, for example, fiber optics, piezoelectric, magnetostrictive, capacitance sensors, and also their installation procedure, which they could be wired or wireless, they could be embedded or surface mounted. So these airborne components must also show that they are functioning reliably with 95% and 90% probability of detection under the environmental and operational condition of an aircraft. Then prognosis is what we do with the data. So the result of the sensor system will be an output where you have to decide whether there is a damage, how do you characterize the damage, and how do you if the damage is located, what is going to be the recommendation to the operator? Do you ground the plane or you're safe to continue? So that's what it feeds into the predictive maintenance. So you need to have a good idea of the extent of damage. How does this damage influence the residual life of a structure? Is it safe to carry operation, or we need to ground the plane and repair it? So it is quite important to include also uncertainties in the environmental and operational condition, as well as uncertainty in the material properties, because if we have to do the remaining life assessment, we do need to have kind of a numerical model or a digital twin concept where you need to establish whether that damage extent is going to result in failure or reduction in a strength of a structure. So you need to run some simulations, and for that it's very important that uncertainties are included and is reliability based analysis. So this until now was really just an introduction of all different components of SHM and in a bigger picture of how they can influence the maintenance of an aircraft, as well as damage tolerant design of composite parts. Now I want to focus on, okay, if we have this concept of SHM, how do we apply it to an existing structure and how do we design for it? So this brings me to introducing the SHARELOC project, which is a Clean Sky 2 core partnership, is a consortium made of made of 8 partners, as you can see, and we at Imperial College are the coordinators of this project. Is really related to structural health monitoring, manufacturing, and repair technologies for life management of composite fuselage. Really, it's a comprehensive assessment of a complete SHM system to date for a composite airframe. It means that every piece of equipment and also installation procedure for SHM components on board have been tested, which covers their integrity, durability, and longevity, as well as also in terms of methodologies, the diagnostic and prognostic assessment. So I will introduce you the components that have been tested in terms of SHM in this project. There are 5 main components. The larger scale, these are the larger scale components where SHM has been designed for them, which is 5-meter curved fuselage panel. There's a flat stiffened panel. There are fittings that has been manufactured by composite, pressure bulkhead joint, thermoplastic window frame. Each of these components have been manufactured with a different manufacturing technology. So, for example, the thermoplastic window frame, we had the stamping process as well as the QSP, which is a new process developed by CETIM, is a quilted stratum process. And really, the idea here is to show all these different components which have been manufactured by different manufacturing technology have to have different considerations when it comes to designing the sensor, as well as the detection algorithms for detecting damage in service of these composite parts. So, for example, the floor beam manufactured by RTM process has different challenges because of its complexity in terms of geometry, as well as the manufacturing process when it's compared to the fuselage panel that is manufactured with automated tape layup and co-cured with the stiffeners in an autoclave. So the idea here was that having all these 5 components in mind, and considering repair for all of these manufactured parts, how do you design an SHM system which can also go towards industrialization of these manufacturing processes as well? So we've looked extensively at different types of sensors as well as the sensing technology. So ultrasonic guided wave, fiber optics, hybrid methods, combined with multifunctional sensors, magnetostrictive sensors, and they've been also all tested following regulations and down selections based on the performances. So it means that starting from coupon and then continuing to element and subcomponent, we've come up with a building block approach where it does the down selection at lower scales with a lot of laboratory tests. And as you go up the scale, you reduce the number of tests and you really focus on verification and validation of each of them. So I will go now through the procedure of this building block that we have developed and really focus, because of time limitation, at the curved fuselage panel, how we got to develop SHM methodologies and technologies, starting from simple coupon test, and how we do the down selection for sensors and installation techniques. So for SHM to be certified as a non-destructive inspection and as a maintenance strategy, first a technology roadmap had to be developed. So within the Sherlock project, we proposed this roadmap, which is really towards the certification of SHM for maintenance. And it's what you can see, for example, different aspect of it in this slide. Important thing to note is that we've done this technology roadmap for each of the 5 main structural items that you saw in the previous slide. So each structural item for us is a part plus sensor. So if we're looking at a window frame, that's a structural item, which is the composite window frame plus the sensors. And the technology roadmap for that is also has to be developed for all these aspects of it separately from the curved fuselage panel, because the material and the manufacturing processes are different. So what we have proposed here is to follow a similar philosophy to industrial verification of composite structure through a building block by conducting SHM analysis and also the associated test at different level of structural complexity. So we start with a small coupon specimen, and we progress through the structural elements and so on. So if we start with coupon elements, you see here at the bottom of the pyramid, we have the mechanical test, where we've done quite a lot of tests for finding the material properties at the coupon level, and it also follows with design and simulation. And at the same time, you also get, we have the same principle for the SHM test pyramid, where we've done quite a lot of tests at this small coupon level, where all these, something like 15 different types of sensors were tested under environmental and operational condition, not just for detectability, but the integrity of the sensors itself. So first, to establish whether these sensors can survive the operational and environmental condition while they are functioning reliably. So that's the first part of the down selection. So this roadmap is specified for each manufacturing technology and each structural part. So it means that different materials, they had different complexities and different design. So if we take the curved fuselage panel, depending on the material that was used for developing the skin, manufacturing the skin and stiffeners, we've done the coupons for the same material and same layup at level 1. Continuing to level 2, which is the element level, means we add additional complexity. In this case, level 2 for us was a monostringer. So we tested monostringer with the selected sensor technologies to see whether the sensors and the installation procedure can function reliably, as well as the detection methodologies. And continuing to a subcomponent level, the down selection then has been made for sensor technologies and methodologies, and the subcomponent level then consists of stiffened panel, which in this case, we had the flat stiffened panel as well as the curved stiffened panel. And it's important to also mention that at the number of tests as we go up the building block reduces, which is similar to the mechanical test block and building block approach, and also the down selection of the technologies has been done based on survivability and the reliability under the operational condition. And the last level in Sherlock, which is going to be tested, is the smart fuselage barrel, which this is going to be done just through a virtual platform. Now, very quickly, going through the technology selection, I'm only going to mention what has been considered in this case, because there is not time to really show all the results here, but we also have publications that are available, and if you're more interested in knowing more about this, I can advise you to go and look at those papers. But the technology selection is okay. The type of sensor, the type of acquisition unit, the type of installation procedure, and as well as miniaturization. So looking at all these different types of sensors, as I mentioned, the sensors that have been used for SHM are numerous. You have fiber optics, you have piezoelectric transducers, and within piezoelectric transducers, you have the different types of piezoelectric. You have piezoceramic, you have the piezo composites such as PVDF. So all of these down selection has been done following the operational and environmental condition of an aircraft, and showing that the sensors can operate reliably once they've been they've been put through cycles of combined loading in terms of temperature, vibration, and load, and putting them through different cycles. Every time you record the response of a sensor, it gives you the same baseline, because otherwise you will end up with misdetection, or your sensors will fail. So these are really taking them through the operational and environmental condition of a flight. And the selection is based on these three different assessment in terms of durability, reliability, and longevity. So following this down selection, for guided wave-based damage detection, which is what I'm going to focus on today, we've selected the piezoelectric transducers here, which is in terms of a smart layer, where we have developed at Imperial ourselves, where you have the protective layer, you have the transducers, and you have the wires that are printed with a thermoplastic bonding layer, which is repairable, this layer, because we can actually peel it off and attach a new layer if one of the sensors have fault. So there is also redundancy in the system. So that's very briefly about the technology that has been selected. Now, how about the methodology development? As if you remember, I developed categorized the SHM developments into early warning and then into damage detection and characterization. So early warning for us can be in terms of passive sensing. It means that the sensors continuously monitor the response of a structure, and they can detect if an external event such as an impact has happened. And by processing the data that has been recorded from these sensors due to an impact event, we can also say something about the energy of the impact. So that can act as an early warning. So only go to the next step, which is damage detection and characterization, if there has been a warning in the structure. Now, in terms of the requirements of this such a system, because aircraft are weight sensitive, we need to make sure that they are lightweight, they are actually low power, and they also function reliably under the environmental and operational condition of an aircraft. So these are really some of the functional requirements of the developed system in terms of the technology, so the hardware that remains on board. Here you see an example of a data acquisition that we've developed within the group, and also an example of a plate that has been sensorized with our diagnostic film, with the connector that is showing you at the end the surface mounted installation procedure. And the expectation of this passive sensing is really to be able to detect the impact event, categorize the energy, locate it, and also assess its severity. So how can we achieve that? There are obviously different ways. Again, very briefly, I'm just going to mention the principle behind the impact detection and characterization is, as you see, sorry, this, I think the video. Okay, this video is not working at the moment, but you can see when there's an impact event, there are guided waves or strain waves that are generated within your structure. And if you have a sensor located at some distance from the impact, you will record these signals. And in the next step is really post-processing. How do you take the information or extract actually the information from these sensor signals? So a lot of work has been focused on machine learning approaches, where you take information features extracted from different sensor signals, and you can then locate where the impact was based on estimated time that it takes for a wave that is traveling from the impact location to your sensor location. And if you have a network of sensors, by fusing this data, you can gather the location of the impact. But at the same time, more importantly, you can also say something about the maximum contact force and relate this maximum contact force to a threshold, which is the delamination threshold. and then categorize your impact based on that. So here you can see at the bottom, these are the C-scan results of 4 different plates manufactured exactly the same with different layup, and they've been impacted with different level of energy. Some of them are low, as you see here, the impact force, which has not resulted in any damage, and some of them are high, where you can see that the lamination has occurred between the plies. So when we compare the contact force to the maximum amplitude of the recorded signals, you can see that there's a direct correlation between the amplitude of the signal and also the threshold, which you see here, the dotted line, which is the threshold for initiation of damage. So really, by looking at it at this level, we can categorize the impact into safe, alert, which is the region which is close to initiation of that damage, and also a red signal, which is okay, there's something definitely has happened and you should ground the plane and really go to the next level, which is active sensing, and it's the damage detection. So localize the damage and categorize its size and severity if possible as well. So this brings us then to active sensing, which really the outcome of this is contributing to maintenance action. So how do you take this damage detection, and depending on which level of methodology that you are able to develop, you will have a different outcome from the active sensing. So again, the active sensing, the functions in terms of the sensor technologies, the sensors remain on board. So again, they have to be weight sensitive and they have to be low power. They have to resist the operational environmental conditions, not just the sensors themselves, but also the installation process as well. And then there can be 4 different levels of expectation from your active sensing methodology. So level 1 is really just detecting that damage exists. Level 2 is detecting the location of damage. Level 3, detecting also the size and severity of damage. And level 4 is really going towards prognosis to say, okay, what is the influence of this damage on the residual strength of a structure. As you can see, as you increase the different levels of the intended function of your active sensing, you increase also the complexity of your SHM system, and also the number of sensors and the location of sensors must also be optimized for different levels of intended function that has been developed. So at the moment, we're going to focus on level 1 and 2, which is the detection and localization. So how can we achieve that for a sensorized fuselage panel by developing active sensing methodologies? As I mentioned, the focus here is going to be on guided wave detection methodology. So a brief introduction of what are guided waves. Guided waves are, as you can see in this video here, are waves that are generated in thin plates, and they travel guided by the upper and lower surfaces of the plate structures, and they travel long distances, but they have, of course, different characteristics. They are dispersive, and the velocity depends on the frequency and the thickness of the plate. The propagation property depends on the material properties that they travel through. So the idea is that when these waves are traveling through the structure, if there is a damage present, the characteristic of the propagation changes. So the waves, they actually interact with damage, and they refract or reflect. And by capturing these small changes in the path of the wave when there is damage present, we hope to detect damage, locate it, and also characterize it. But of course, there are different aspects of the guided wave that we need to bear in mind when it comes to designing an SHM methodology. First of all, they are multimodal, so there is different modes, symmetric and anti-symmetric mode. These are with respect to the mid surface of the plate, and they have different properties. How they propagate through the structure, different velocities, and so on. I'm not going to go through the details of it, but here is an example of a full wave field measurement with a laser Doppler vibrometer, where you can see that excitation at different frequencies, 50 kilohertz or 250 kilohertz, which is, excites different modes as dominant symmetric mode or dominant anti-symmetric mode. You see that they have different wavelengths. They interact with damage very differently when you compare the A0 and S0 mode. And depending on the thickness of the plate, the type of damage that you want to detect, you can actively excite the structure given with the given A0 or S0 mode. So these are really the characteristics of the wave that you need to have in mind and consider. But most of the detection algorithms are baseline methods. So it means that when you sensorize your structure, you actually record the baseline at a healthy state. So you know when there is no damage, you record the response of a structure. And after a while, you at current state, if you want to detect whether there is damage or not, or check the integrity of a structure, you retake these measurements and you compare the current state with the baseline state. So this means that if your guided waves that are propagating in the plate and then you're recording it, if they are sensitive to operational conditions such as changes in temperature, changes in load or background noise, these changes can be mistaken for damage if you don't correct for it. So that's why it's very important to study the effect of guided wave, especially under the temperature differences, because the effect of temperature can easily be mistaken for the effect of damage. So this really takes us to the process that we've developed within Sherlock, which is a building block approach for SHM verification, where we've tested at the SHM development at Coupon under environmental and operational condition, developing the factors for this. So if there are compensation factors for temperature, can be developed at material level at Coupon. They can be updated at the monostringer with different complexities of having a stiffener, for example, bonded to the skin, and then verified at the last level, which is our subcomponent level for detecting multiple damages. So this is very briefly showing these different levels. And in a second, I'll just go quickly through how the development has been done in terms of detecting damage at the subcomponent level. So this is just showing an environmental chamber for the flat panel where we've taken the measurement at different temperature variations just for the verification and validation. And this is a coupon that you can see again in an environmental chamber, but the range of temperature that we've taken at a coupon level has been much more extensive. So going from -40 to 80 degrees, whereas as we go up the scale, we have reduced the number of tests and the range of temperature changes, and we've used it as updating the factors and or just verification and validation. So this is again very quickly in terms of the numerical analysis that has to also go alongside this building block approach for SHM verification, because at the end we're going to have a virtual platform. So in this case, it is really a calibration of damage parameter based on experimental data, and it's using statistical analysis, so basing, updating. There's no time to really go through all aspects of it, but just to mention that this the mechanical and experimental testing has to go combined or side by side with this numerical development, which we've developed a digital clone, which is to have all these recalibrating parameters, and every time a new experiment become available, we update this to increase the reliability of the detection. So really, just very quickly about the effect of temperature and vibration on the signals. You can see an example of how signal is affected by temperature changes and also vibration. So it's very important to be able to compensate for it. What we have done is, again, following building block approach, we developed compensation algorithms for temperature at coupon level. And as we go up the scale, we have updated it and verified and validated it for different scales of the test. So really, the damage detection is based on how you process the data, the pristine and the damaged data. So by introducing a damage index, we developed a threshold for a pristine state, and this is a damaged state. So you put your detectability threshold somewhere that is way above the noise threshold in your data. And also, after compensation for temperature, you need to ensure that the damage is really detected reliably. So this is the first level where we've detected damage based on damage indices. And really, going up the scale, you can see here for the three different levels of coupon, element, and subcomponent, we've introduced the damage index, where it detects reliably damage being present given a threshold. So this threshold setting has to include a lot of uncertainty as well, so is reliability based. So again, if you're interested in knowing more, I refer you to our publications. Just for the interest of time, I want to go through the last two slides very quickly. So putting everything together, level one really is focusing on detection. So the result that you see here based on the Mahalanobis distance is detecting damage that exists in coupon subcomponent, element and subcomponent. So combining the threshold for all of that, which has been developed at a material level, we can have a very good detectability, because the false positive rate here, you can see that it's 0.1. And level two is then localization. There are very, established localization algorithms such as rapid, delay, and sum, some combined with weighting residual. So we've used, we calibrated some of these imaging algorithms to detect impact, but also to be able to detect multiple impacts. So by grouping the sensors, you can see here that we've detected multiple impacts, and these are the result of damage localization at the subcomponent level, which is the flat stiffened panel. Once you've detected your damage, then of course the next level is to do the residual remaining useful life analysis, which is the prognosis, and at the same time the residual strength, which you can see here. There's an actual test that has been done, but also we have to combine it with numerical simulation, where you include uncertainties in the material as well as load and so on. And you can then set your detectable damage threshold based on reduction in the ultimate load. Now, we are at an exciting stage at the project where we've just impacted this 5-meter long fuselage panel. So here I'm just showing the C-scan result of the impact. And really what we are waiting to do now is to follow, put this panel under environmental conditioning. And the next stage of it would really be to do a full-scale test in this very complex machine there, where we do compression after impact, tension after impact, and so on, to get the residual life of a structure. And once we have that result, then of course we can feed that for verification and validation of methodologies and technologies as input into the virtual platform. So that's really the up-to-date progress of the SHARELOC project, which is developing SHM methodologies and technologies towards industrialization of SHM-enabled smart fuselage. Here I just put some conclusions and the way forward to just emphasize that, of course, there are aspects that are still needs development, especially reliability, probability of detection, miniaturization of electronics on board, and more importantly, there has to be a cost-benefit analysis. So if you want to go to an airliner and convince them to take SHM on board of an aircraft, you need to have a cost-benefit analysis for it. So these are all that at the same time we are developing and progressing within Sherlock. So sorry, I had to rush a bit through, but most importantly, at the end, I'd like to thank all our PhD students and research staff who have contributed to everything that you've heard today. So thank you very much, and I'm happy to answer any questions that you have.
Thank you, Sarah, for the very interesting presentation and for sticking to the time. Much appreciated. We do have a couple of minutes left to answer questions. So if you have any extra questions, you should have a tab where you can ask attendee questions. And then the format is that I will read these out and ask as many as we can from our speaker. Can I start with a general question? It's very impressive, obviously, to see these methods being used on a 5-meter panel. What do you think are actually the next steps needed to get this actually onto an aircraft? And how long, in terms of time, would you expect that to take?
Yes, that's a good question. So I would say, really, if I go back to the slide that I was showing, at the moment we are developing the numerical models at the same time to be validated and verified, because of course experimentally it's very expensive. We have 3 such panels to test within Sherlock, so this was just the first one, but experimentally there's a lot of I would say constraint to even have an impact tower on top of this panel is quite challenging. How do you ensure that you are consistent with impacting it to cause only barely visible impact damage, and also testing it at a full scale in this sophisticated test machine is also very costly and time consuming. So it's important to establish the numerical models at the same time to include uncertainty in the development. But I think really the next step is, if we are considering the industrialization, we need to show repeatability. So if we have one panel and we have 72 transducers on this panel, sometimes it's challenging because it's at the moment the installation procedures, as much as we even try to make it very industrial, it's still if one of the wires are slightly wired differently, soldered differently, you can see that the amplitude might change, or if the length of the cable is different. So there are a lot of parameters that influence the signals that has been recorded. So we need to make sure that there is always reliability and repeatability in the data that we are recording, because if any change in amplitude, if not compensated for, will be mistaken for damage. So there is no good to have an SHM system where you will, every time you fly, it will give you a false alarm saying there is damage detected, because just the changes in the data can result in change in damage. Or worse than that, if we don't find the damage changes and mistaken it for environmental effect. So I think the threshold setting is very important, and really we have to focus on the technology which is going to be repeatable and reliable, not just the data processing, but really the sensorization of the panel has to go towards the industrial standard. Otherwise, if it's also interrupting the process, so this is something we've always had in mind when it came to in Sherlock project in terms of down selection of methodologies. Does this interrupt the industrialization process? So if it's embedding of a fiber optic in a panel, is this going to be possible for a full barrel, which is one shot and is going to interrupt the manufacturing? So that's just to bear in mind.
Okay, good. Thank you. We've got quite a few more questions coming up. Can I just add on to this? We had a question coming in about the added cost of putting these sensors on a panel compared with a panel which doesn't have any sensors. And I guess maybe if you could also comment briefly on the weight that adds, which obviously for aircraft is very important.
Yes, so there's a paper we are waiting for it to be published with our postdoc Ilias, and he's done quite a wonderful job in looking at the cost benefit of having SHM on board, and he has compared the cost in terms of added weight, but as well as of different sensor systems. So all is guided wave-based SHM systems, but with wires, with printed wires. So one of the reasons we've developed this diagnostic layer and print the wires on top was because the actual wires were very heavy, and we've realized from the previous projects in SARISTU that it's something that is not acceptable, because it's any weight savings you do, you compensate with SHM, you're just going to add extra weight on. So the layers that we print the wires on are very light. They hardly have any weight, but at the same time, we've included the cost of that in terms of fuel, extra fuel that you need. And we've figured out how many years of operation you actually need to balance the cost of SHM versus the maintenance cost. So it's not something at the start you can say, oh, well, this SHM is going to be cost effective. No, you have to have extra cost at the beginning for the sensors, but in like 10 years time, you will see the benefit of having SHM on board. So hopefully the paper will be out soon, and I can refer you to that.
Okay, good. Thank you. Let's just actually start with some of the earlier questions which came in, which was about, was there any consideration of how you incorporate product quality of the composite component, for example, porosity, and its impact on integrity when you design such a system?
Yes, so that's why I mentioned at the beginning that we've looked at different manufacturing technologies. So some of the components were made with higher quality just because of the manufacturing process and the partner that has been involved in the manufacturing. So we've had, for example, liquid resin infusion for the floor beam, and that has been, it hasn't been so easy from the beginning of getting these cross sections with very good quality. So you could see a lot of waviness, dry spots. So we've tailored the SHM for those type of defects that can happen based on the manufacturing process as well. So for a fuselage panel, really the defect that you have to worry about is impact event, and really impact at the foot of the stiffener, which could be quite catastrophic. So we've, at lower scales, at coupon level, we've looked at embedding of fiber optics as well. So when it was an embedded fiber optic, we've done mechanical tests to see whether there is any strength reduction based on embedding of the fiber optics. So we've done, mechanical tests to ensure that integrating SHM hasn't really reduced the mechanical performance of the part as well. But at the end, I think the down selection was done for surface mounted, just because if there's a failure in the sensor, you can actually replace it. Whereas if you go for a one shot fuselage barrel and your fiber optic in the middle has broken, you cannot replace the barrel.
Okay, thanks a lot. We have quite a few more questions coming up and not much time left. We have a couple of questions to the considerations for the SHM system. So one question was from someone who has experienced temperatures outside, obviously, of up to minus 65 degrees Celsius, while you only seem to consider up to minus 40 degree. Has this skin temperature been determined from actual operational statistics, or what was the reason for choosing this?
Yes, so we focused on regional aircraft aircraft, and according to the standards, regional aircraft goes for, I think, depending on type of climate within Europe, is classified as -40 to +80. But I just like to mention that of course the aircraft can go experience different temperature as well. What we focused on is that at the moment, especially in Sherlock, what we have developed the SHM for is for maintenance on ground. So especially for the guided wave-based system, we don't expect to excite the structure while it's flying, but every time it lands, we excite the structure. So there is, these are conditions of on-ground temperature changes that can be -40. And also the sensors are integrated from the interior of an aircraft. So it's not on the outside. So there is slightly, temperature difference. And we have the protective layer on top. So it is quite challenging if the aircraft is flying at -60 degrees of temperature to say that, guided waves is going to be recorded. So our passive warning system is going to be working during flight, and the active warning, which is the guided wave excitation, is on ground. There is no limitation for the system not to work at -65. We've tested it for more extreme temperatures, but for the purpose of this project, we focused on really the environmental condition within Europe. But it is -65 will also work, in my opinion. The sensors will function. It's not a problem.
Okay, thank you. We have a related question to this. On how the temperature and moisture has an effect on the detection of the damage on the test panels.
Yes, so the temperature has an effect as well as moisture in changing the propagation properties of guided waves. And these changes are in terms of phase change and amplitude change. So what we've done is we've developed functions which describe these phase and amplitude change for guided wave propagation at a coupon level as a material characteristics. So as long as that's why we call it the building block approach. As long as the higher scale of the building block have the same layup and the same material as the lower building block, we want these compensations to be material characteristics, so that you don't have to repeat all the tests at the lower at the higher levels of the building block, where your structures are much more complex and they are larger and more difficult to test it in environmental chamber. So really the effect of temperature and moisture is with guided wave is in terms of phase change and amplitude change. Now, what is the long-term effect of moisture? What we've done is for the subcomponents, we've exposed them to environmental conditioning, where you take it to 70 degrees with 80% moisture, and then you leave it there for a while until it's saturated. You take it out and you take the data. We managed to compensate for it and detect the damage reliably, but what we haven't now, we are waiting to test is we've had coupons with sensors on them, and we've left them in the environmental chamber for 3 months to really saturate them, and then we want to take the data to make sure that it also doesn't affect the installation if it's a long-term exposure, because it's different if you expose it once or if you do it in a cyclic way.
Okay, thank you. And we've actually got a question very much related to this, talking about the sensor reliability for guided waves, whether you have actually looked at including 2 elements per sensors, so that in case of a dead element, you have some reliability and redundancy in the system.
Yes, so what we've done is we have developed optimization algorithm for optimizing the location and the number of sensors, and this optimization does include sensor failure. So we've also have what we call self-diagnosis. So before every recording or every acquisition, we check the EMI measurements of the sensors to ensure that the sensors itself is healthy before we record the data. So that this increases the reliability of detection by ensuring that the installation is okay and the sensor is okay. Once the EMI measure shows the sensor is healthy, we do then go ahead with the guided wave recording. But we've also shown through the optimization that if one sensor fails, you still are able to cover the area that you have under inspection still reliably. So we've had included the redundancy in the system.
Okay, good. We have a few more questions. I probably need you to speed up a bit because we're already exceeding our time limit.
Yeah.
The next question would be on the decision or material selection for the sensors, like the ones you had integrated in the plastic film.
Yes.
How did you come to this decision?
So we've selected the ceramic piezoelectric transducers. These are, from commercial providers off the shelf. We didn't manufacture the sensors itself. This PI ceramic company, they do Durac transducers as well. So these are well-established sensors that have been tested by different groups. What we've really focused on was the installation procedure. So the thermoplastic film was quite a bit of a study to find the film which cures at a temperature which is above the operational temperature but still below the curing temperature of the composite itself, so we can repair it, so we can remove it and reattach it. But the sensors itself, they are PI ceramic normal sensors. We've not developed the sensors ourselves. We just check that the operational range is acceptable.
Okay, thank you. And we have a couple more questions for the guided waves. One question is how the ultrasonic guided wave damage detection, how does it react with different connections such as rivets or bolts in the structure?
Yes, good question. Well, we've not within Sherlock, because Sherlock is related to composites, but with other students, I've looked at rivets or bolts, and really to detect cracks that initiate from the rivet hole. It's possible to detect them. However, if you want to really monitor crack growth, you have to put quite a lot of sensors around that area, so it becomes more like hotspot monitoring. In other ways, if you want to detect cracks in metallic, it's the challenges are different, but in a way it's easier to detect reflections from a crack because it is a really discontinuity in the structure. Whereas in composite, you have delamination between plies, and it's much more difficult to detect or challenging to detect that type of damage. But yes, for bolts and cracks, you can. Bolt loosening, I'm personally a little bit suspicious. I've tried it. The bolt has to be completely loosened for you to detect it. I know there are researchers out there that they say it works, but from my personal opinion, loosening of bolts, unless the bolt is missing, it's really, the threshold is very narrow.
Okay, thank you. We've got a follow-up question on this, that some damages can be easier to detect when they are under load. So on the ground, is that a possibility to, and how would that affect the detectability of the system?
Yes, that's very good. So things like kissing bond, for example, is still very challenging to detect, even with guided waves. So I will have no claim on us being able to detect that with reliability. But we've tested it with, so this is something that we are going to, we're very much looking forward to see with the large scale panel test, because the curve panel now is going to be tested under load. So we will close the barrel and apply compression and tension. So we really hope to be able to answer this question in the near future with experimental evidence that we are able to distinguish, still the effect of damage from the load that is in the structure.
Okay, good. Thank you. We have two more questions to go through.
Yeah.
One is about for the guided waves for the simulation, whether you used high performance computing and if there are any advances in this respect.
Yes, so for the larger scale, so the the subcomponent level, which is the Stephen panel, of course we used HPC. Those are done. The results, I think, the ones I showed, they've been done with Abacus model, but it is quite time consuming and difficult. But at the same time, we also have done guided wave modeling with boundary element method, which is like an in-house code. We have some papers published with that as well. It is, of course, it's not a commercial code, so it has its own challenges, but in terms of time consumed, the resources, it is much less demanding. But the ones that I shown here, the simulation have been done with Abacus Explicit. Abacus Explicit, only consideration you need to make is that there are no piezoelectric elements in Abacus Explicit, so you need to do the excitation and sensing with equivalent displacement.
Okay, thank you. And the final question about for general view, what do you feel for the feasibility to apply this across other industries beyond aviation, so marine structures, rail construction?
Well, I would say, to be honest, the aeronautics and aerospace, because I also have a project now with ESA, which they're looking into using SHM for reusability in vertical launchers. This is the most challenging one because the safety requirements are really high, because the stakes are really high. Whereas SHM in bridge structures or railways have been used in practice for years. Their challenges are very different. The structures are more static and less dynamic. So in other disciplines, they've been, I would say, in even offshore, for oil and gas, for some of the pipes, it's been established, more established than in aeronautics. For aerospace, still it comes down to the reliability of it. Can you actually ensure the safety of all these passengers if we're relying on data coming from sensors? So I would really say that other disciplines, engineering disciplines, are more established than aerospace, just because the safety and the stakes are lower than in this scenario. So going forward, really the focus should be, can we really show that 90-95% reliability and probability of detection?
Okay, thanks a lot. I think on this, some things I've omitted from the question was people thanking you for the very nice presentation. And I would like to echo that and thank you again for taking the time to give the presentation. I hope everyone found this interesting. Apologies for running slightly over time, but we wanted to try to answer as many questions as possible. So thanks a lot for joining us, and we will hopefully be having a couple more webinars coming up over the next few months. Thank you, Sarah.
Thank you very much. Thanks everyone for their attention. Bye-bye.